All right, let's get started. Do we have any questions before we begin? Hold on. We're gonna go through a lot of stuff for the exam. Any non-exam questions? Hopefully by now you have submitted homework number 3. If you haven't, you have probably, I would guess, about 5 minutes to submit it, where it would be late. After that, when we start reviewing things in this class, it's going to be a 0. Like I've warned several times before. Okay, so plan for today. First, I would like to go through exam number 1 instructions, right? Just so you guys can all get familiar with that. After that, is there a glare again? Let's do that. All right. After we go through the instructions, you guys can ask me questions about how the exam is going to work as a format. After that, we're going to do review questions. I got 1 request, maybe 1.5 requests for problems to review. So we'll see if there's anything else you guys want to go through. Okay. So exam number 1 instructions are going to be up on Blackboard probably later today. I want to say at some point, if not by tomorrow. So you guys will have access to these ahead of time, right? The exam, these will also be printed on the exam, but what I would recommend is to familiarize yourself with them before the exam. That way you don't have to read this page during the exam, right? So exam is on Monday. We're going to try and start at 12 o'clock exactly. So if you can show up a few minutes early so I can hand you the physical copies, that'd be great. The end time for the exam is going to be 12:45, not 12:50. Okay? So in-person exam, you're going to come here. I think there should be enough seats for everyone. I counted them out earlier. No online option is available. If you've taken classes with me before, that's how I used to do it. Not this time. So before the exam, show up a few minutes early. I will hand you your physical copy. You are not to look at it beyond the first page. You can put your name down. That's about it. If I see anyone looking at it, 20 points off right there. And then I guess you can get started early if you want, but you're going to be in trouble at that point. So I will say I'm very much a stickler about these minor things, right? Submitting things on time. When I say you're done, put your pencils down, that sort of stuff. Okay. For the exam, cheating obviously will not be tolerated. Don't work with other people. Don't copy other people. No calculator, no phone, no digital devices of any sort, whatever. It is open notes, though, an open book, right? Printed open notes, right? Not an iPad. Print them out if you want. I recommend getting a study sheet ahead of time, though. I also recommend that you familiarize yourself, because if you're going to take this exam where you read through all your notes and stuff like that for every single problem, you will not finish, at least in my opinion. I think that for this exam, there's 3 problems I want to say. I bet we'll get somebody that finishes under 20 minutes. Probably like a third of the class at least will finish, I would bet, before time is up. And then the rest of you guys will probably be pushing all the way to the clock. That would be my bet here. So I think there's more than ample enough time here. But some people like to use that full amount of time, but don't rely on your notes too much. Have like a study sheet or something is what I would recommend. Who knows? Last time I gave this exam, people did really, really well on it. But that was also having an online option. So we'll see what happens this time. If I can't clearly read your answers, you won't get credit. So the TA is the one that's been grading the homeworks primarily, and I just kind of like check it over with her every once in a while. I'm a much more strict grader than the TA. She is very nice. I am not. You need to make sure I can understand things very clearly, box things out, right, for your final answers. If you're certain that you wrote something down that you don't think is right anymore, you cross it out and put something else there, right? Make it clear, right? Don't leave things up to me to guess what your final answer is or not. Sometimes I will be merciful with that. Other times I will not be. Okay. Make sure to number the problems clearly, show your work, box your final answers. For problems that allow partial credit, that's another difference from the homework, right? I'm not grading off of effort here anymore. I'm grading partial effort on how you understand the concepts for the problems, right? As well as your final answer to an extent, right? But I'm going to go through these problems bit by bit to see, what you get right and what you get wrong, right? I recommend you follow the steps outlined in class, right? There is a little bit of deviation for that, of course. But if I say use a Laplace and inverse Laplace transform to solve something, you don't use integration by parts or something like that, right? Use the Laplace transforms. All right. I will give you a Laplace transform table in this exam, at least on like page 2 or something like that. If you can keep your problems in order, I know that's not always going to be perfect. I will provide extra paper if necessary. Hopefully there will be enough for you guys to work with, but if you need more, you can have more. If there are any extra kind of problems, there aren't, so that doesn't matter. Submission, finish early, you just come up, hand it to me, and that's it. At 12:45 or after 45 minutes, if we get a late start, hopefully not, you stop writing. I'll probably have like a clock or something out up here to intimidate you guys or something like that, but really to give you guys a sense for how much time you have for the exam. The second I say you're done, put your pencils down. If I see that somebody's still writing after that point, again, 20 points off right there. And then between 12:45 and 12:50, we're going to have like an orderly, you guys come up and hand me your exams and leave and stuff like that. If you need staples, I'll have a stapler for you and something like that. So that won't count towards like your timing and stuff like that. All right, that's pretty much it for how this exam is going to work. Questions? If possible, right? Like, I don't want to have to go to page 2 where you start a problem for problem number 1, and then you say, turn to page 4, and then turn to page 6 and stuff like that, right? Like, be orderly as much as you can, right? Like, I get it. Sometimes you're going to go through problem number 2, let's say, and you get halfway through and you're like, oh, I did this wrong, and I need to use my extra sheet at the back of it. So you say, refer to that extra sheet. That's fine. Just try and make it orderly. Try and make sure I understand what problem you're working on and stuff like that, right? It's nothing crazy. No calculators at all whatsoever is the second question there. No digital devices of any sort. All right, just you, your mind, your paper. I would say the homework and the class examples, what we've done through in the class, those are probably your best bets to learn like how I build the problems and stuff like that, right? It's not going to be just a replica from the homework though, of course, right? Or maybe it will, who knows? Maybe I was nice, probably not. Any other questions about how this exam is going to work? All right. I expect you guys will do pretty well here. I think you guys should be pretty strong at this sort of stuff. Just don't get in your own heads is what I would recommend. Just manage your time well, and I think you guys will do okay.
Any other conceptual, there be any questions like state the
definitions and stuff like that? Not on this one, at least. No, I don't think so. It's been a while since I built the exam, but no, it's more like engineering problems, similar to the homework, similar to the class examples, that type of stuff. Any other questions?
Is the final
There will be plenty of partial credit available, right? But the final answer will be important itself. Okay, anything else? Yeah. Yeah, so the exam is pretty much like the first 2 pages are the front sheet and the instructions. I think that's the first page. Second page is a Laplace table. Third page is blank. Then 4 and 5 are the problem, and then a homework or a blank page rather. And then problem, blank page, problem, blank page, a couple extra ones. And then I'll have extra sheets up here where I can go grab them if we need them. All right. I don't think you guys will need it, but who knows? Any other questions? All right. Again, I think you guys should do well. Just don't get in your own heads and you should be fine with this stuff. All right. The rest of the class is for you guys, right? I don't have anything prepared in particular here, right? We are just going to review any questions that you guys want to go through. If you guys don't want to go through any, we're done for the day. I don't care. This is an optional class in the first place, right? It's just a review class. I don't care. The requests that I've gotten so far is homework number 3, problem number 1, which I don't think we're going to have enough time to go through in full here, unless that's the only thing that we're doing here. But maybe we can at least talk about it.
The exam still next month.
Yep. It's on that sheet, February 20th, right? That's next Monday. Yep. Any other problems? I think
Unit step modifier.
Unit step modifier. I have no idea what you mean by that.
So like very first one, it was probably the second question, but it was the has a factor of 4 or
Okay, yeah, that, all right, that one will take a second. Yeah, we can talk about that. Homework number 2, problem number 2, but just in particular the setup. Right? What is it? I don't even know what that problem is. Oh yeah, mechanical modeling system. Yeah, sure. We can talk about that one. Homework number 2, problem number 3, the setup. Oh yeah, that one's nice and clean. Homework number 2, problem number 2. So we got another vote for that. Anything else? Remember, we only have like 40 minutes or so. I'd go longer, but I think we have a class directly after this one. So let's start with this list at least. Let's talk about the unit step modifier. If I say it's a step with a magnitude of 4, you multiply the step by 4. That's all it is. It's a constant, right? That's what a unit step is in time, right? So if I say I have a step of magnitude 32, what is U of t equal to, and what is U of s equal to? $32, right? The step is just a constant. They are the same thing, right? Technically, a step, the only difference between that and a concept is that a constant is that before time is equal to 0, which we never deal with in this class, a step is 0. After time is equal to 0, it's a constant. That's it. That's all I'm saying, right? Right? A unit step, the unit comes from, it's a magnitude of 1. If it is not a unit step, then it is whatever I say that magnitude is. That's it. Right? Okay? It's a constant. Step magnitude of whatever, that's just a constant. Okay. Let's see here. So I know that homework number 3, problem number 1 was requested first, but I think that maybe to kind of build up towards that, let's try and go through numbers 3 and maybe number 4 here first before we get to that one. So let's talk about homework number 2, problem number 2, which was the most popular one here as well to begin with. So what I believe for this one was, here's our figure. We have a spring, we have a damper, we have a mass with a force that's acting on it, connects to another damper here, and then another mass, right? These dampers are both C's, the masses are both M, and we have a spring constant K here, and we want to get a transfer function where this is our input, right? Which I won't always state, but I think that's kind of obvious. That's what our input is, right? It's our external force, and the output is the velocity of the first mass. I think some people were confused about this, but I tried to clarify it. This is V1, our output, Y, is 2.5 times V1, right? 2.5 times the velocity of that first mass. Okay, and we just want to get a transfer function for this. No gravity, no friction. It's typically how this will be. So how do we go about doing this? Yeah.
Can you explain why that velocity is being multiplied by 2.5?
Just to change the problem so it's not just straight up velocity as the output. That's it. Right? Maybe there's a context where it's that velocity is being transferred into something else, and that's what you're actually measuring or something like that, or that's what you're actually concerned with. For this, it could be like the equivalent of like a force term, potentially, depending on what the units of that 2.5 is. But there's no rhyme or reason for it here. It's just to not have just a 1 on top for our transfer function, just to make it slightly different.
Oh, sorry, I was going to say this.
Yeah, go for it.
Assign your directions.
All right, so that's what I recommend doing, right? I would assign some directions here. Let's call this X1. Let's call this X2 and V2. You guys would probably also say this is X1 dot and X2 dot, right? Right, those are probably the major directions that we need to deal with for this problem in particular. Okay, and then we do our free body diagrams. That's for the one on the left. And that's for the one on the right. Okay. So what do we get here? What forces are going to be acting on those masses? Okay, spring constant, right? How do we figure out what our forces is, right? Again, what I like to do is I hold all the masses still except for one. It's like pretending I'm like pushing down on them so they can't move at all, right? Then I take one and I move it in its positive velocity direction, which should also be its positive like displacement, right? If you assign your coordinates properly. And I see how forces react on all our system, right? Our entire system rather. So let's take that mass on the right, make it stand still, walk it down, right? Staple it to the ground, whatever. Then we move mass 1 to the right at a rate of V1 and by an amount X1, a generic amount, right? You could say it's 1 meter, but it's an amount X1. Why did you decide to assign the X direction, the opposite direction of the input? So I think it depends on the context here, right? For me, it makes more sense for me to just assign all my coordinates going in the right direction. You could absolutely assign your velocities in the left direction here. The intention for this problem was I meant velocity in the right direction. I was just kind of vague here, right? But you could do it and just convert it with a negative later on, right? It's totally up to you how you do that, right? The coordinates don't matter that much as long as you're consistent and then you get the right output at the end of it, right? So I know a lot of you guys instinctively want to go with the same direction the input force is. Let me try and challenge that for you guys right here and just not do that. Because I think a lot of you guys think in terms of like the input force is the thing that's going to control our direction and stuff like that. But that F can be negative, right? I could just say it's a -5. And there it is, right? Think about in terms of how you want to define it then. Okay? So let's try and just work with these directions for this time. Okay, so what kind of forces do we have acting on our system? We had a spring, somebody said that, right? Where, what amount? So on the left mass, right, we'll have that spring force, right? And what's that spring force going to be? Kx1, right? Right, not X. There is no X here. It's X1, right? Why is it going to the left? Because the spring is trying to resist our positive direction of motion, right? Or displacement. Okay, what other forces do we have acting on our system? What was that? Damper, okay. What are the dampers doing? We have 2 of them.
The one at the left hand is this foot, somewhere as the spring, and the one at the right.
Okay, so let's do this one here. What's that force going to be? Force of a damper. Cx1 dot, very good. Okay, what else? It's going this way. You guys agree with that? If I move this mass to the right, and we have that dash pot, right? A damper is kind of like, you know, those doors with like the air things on top. I forget what they're called, dampers. You know, the hiss and all that, right? So if I move our mass to the right, is that damper going to help it move further to the right? No, right? It's going to, again, resist that. Right? The damper and the springs, they always try and resist what we're doing here. Right? And so what's that force going to be? It's going to be Cx1 dot again, right? X1 dot, that's the rate of change we're moving this mass here. The damper has a coefficient of C, and it is still resisting. right? What other forces? We have F here, right? Anything else going on? Well, so this is how I like to break it up, right? You can do it that way if you're good enough to skip ahead, right? But what I like to do, right, is I'm almost done with looking at mass one's positions, and then I'm going to move mass two, and that's where that term will come into play here. But you're absolutely correct. We'll see it in just a second. All right. Any other forces that happen by moving this first mass to its positive velocity direction? Right? The damper over here, we have equal and opposite forces between these guys. Because this first mass is moving to the right, it's going to try, that damper is trying to get itself to stop moving. So what does it do? It tries to move the other mass to the right as well, right? It tries to force it this way. Okay. Now we've done all the forces that are acting on these two. Now let's talk about the second mass. So now I'm going to lock down the first mass, staple it to the ground, right? And move the second mass, the one on the right, in the positive velocity direction. What forces do we have acting in this case? CX2 dot to the left of mass 2, I agree, right? Right, due to this damper, right, that mass is going to move to the right, that damper is going to try and stop that movement. Okay, any other forces? Right, the first mass, this damper, right, it's going to try and pull this by an amount with a force CX2 dot, right? Again, the damper is trying to stop its own relative motion here, right? And so that's where we would get the C times X1 dot minus X2 dot, right? I'm looking at those two as separate, right? But if you know how this stuff works, you could just combine these terms directly together and skip a step, right? What do we do from here? Equations of motion, right? Newton's second law is the big one, right? So Newton's second law states M X1 double dot or V1 dot, depending on how you want to do this problem, is equal to what? Sum of our forces, right? What are the sum of our forces here? We have that negative F, which is equal to U, right? Negative U, negative KX1, negative 2 times CX1 dot, and plus CX2 dot. Right? I'm just looking at the arrows and how they compare relative to positive velocity for our mass here. We'll go with that. Same thing for the other one. It's a little bit easier. MX2 double dot will just be CX1 dot minus CX2 dot. Right? What do we do from here? Yeah, question.
Are we going to get a sign error somewhere? We have
I would not argue it's a sign error here, right? So I would say if I haven't specified what the positive velocity direction is, or the positive, well, I'm always going to specify what the positive force is, right? But if I haven't specified like what velocity output I'm looking for here, then I think you could come up to me and argue that having a negative there or not having the negative there, that's perfectly okay, right? Now, if I specify, I say I want my output to be velocity pointing to the right, where that's a positive right direction, then we're not going to get a sign error, but we're going to get a negative somewhere in here, right? Because of that, F is equal to U pointing to the left. All right, so I would not say that's a sign error. I'm just saying we'll end up with a negative sign somewhere, right? Okay, what will we do from here? I don't think we'll spend the entire time going through this, but I think the major question was the setup, right? Does this cover what you were looking for? Mm-hmm. Okay, so after this point, it's just algebra. So granted, it is a little bit complicated for the algebra, right? But what will we do here? We do a Laplace transform, right? Is that what you guys were about to say?
Or I was gonna say this.
All right, what's the next step?
The right hand side equation you say, well, x2 have your Laplace going.
So after the Laplace transform, right? So let's do a Laplace transform of all this stuff for both of these equations, right? And it depends. Do you guys want to work in terms of velocities or do you want to work in terms of the x dots, right? So technically what we're looking for our output is 2.5 times x1 dot. That's what we're really looking for here. So let's do a Laplace transform of these guys. No initial conditions. Right? Anywhere there's a dot, you replace that by an S. Same thing with this equation here. That'll be an S squared. Right? From here, what we can do, your suggestion was to solve for x2 using this equation in terms of x1. I'm just moving the x2 over to the other side. Right? And then I'm going to solve for x2 of s. This is one way to do it. It's not the only way to do it. Right? And we could see that actually those s's would end up canceling out. All right. What do we do from here? Probably combine these two equations, right? And solve for x1 of s as a function of u. Right? So I'm going to move all the x1 of s terms over here that we have so far. Then we have u of s with a negative in front of it. And then we have cs times x2, which was this stuff. Right? From here, we move this x1 of s times all this junk over to this side. Right? And then just solve for x1 of s. Right? Or more particularly, solve for x1 of s over u of s. Right? Once we get here, right? Does anybody need me to go through that stuff? That's just algebra at this point. What I would probably suggest is multiplying everything by this term. Well, I guess I would cancel out the s's. Multiply everything by this denominator term and shift it over. That's a little bit easier for me to work with, right? But it depends on what you want. Yeah.
So at that point, that transfer function, also I did like x1 s over fs to
S x1 s over f of s. Yeah.
that'd be-
Yeah, as long as you simplify things, I think it should be okay, right? Personally, for me, I like to be a little bit careful. I take this step by step. So when I see these equations, I think to myself, just solve for x1 and then worry about getting what the output is after that, right? You're trying to skip a step and go straight to the output. I don't think that's wrong necessarily, but I bet you're going to need to multiply or divide by an 1 over s somewhere at some point, right? And then you got to make sure you simplify it down properly after
Well,
that point.
My approach was I just solve for displacement that's easy for me. Then once I get displacement, I just multiply both sides as. You know what I'm saying?
Displacement, do you mean net deflection?
Well, I'm solving for x1s,
Mhm.
not velocity, not v1s, you know what I'm saying?
Well, you're solving for x1s, right? Or are you solving for s times x1 of s?
Or.
Well, we're getting down a rabbit hole here. I'm going to just explain how I do this, right? We solve for x1 over u, or x1 as a function of u, right? And then what is our output? Take a Laplace transform of this guy over here. Laplace transform of y is equal to 2.5 x1 dot. Y of s, 2.5 s x1 of s, right? So if we can solve for x1 of s, then we can get our output equation here. Right, and I'm happy to go through the algebra and go through step by step with you guys to see how I got my answer, right? Maybe you got the same equivalent answer, right? And it just didn't happen to be in the same format. And if that's the case, you can come talk to me, and we could see if we can give you guys points back. But this is my general procedure for what we're looking for here. Any questions on this? Yeah. So that's what he's asking, I think. So you could keep it in terms of s times x1, or you could keep it in terms of v1 and v2, right? With the v1s and v2s, you're going to be dealing with extra equations because x2 dot would be v2, right? And now you're dealing with 4 equations to solve instead of 2. Okay? It would end up being the same thing either way. I would not do it I would not transform this stuff into V until after the Laplace transform. That's what I would recommend. Personally, for me, that makes it a lot easier, right? If you start doing integrals in time domain for these representations, I mean, it'll work out, but it seems like there's a lot more options for making mistakes at this point. Okay. Cool. So is that 2.5 times x1 dot or 2.5 times v1? Is that what you gave me at the end of it? Right? Is that the transfer function you gave me? Did you give me an output that was v1 times 2.5? No, then of course it's not right.
When we're presenting a final transfer function, there's certain way you want to do it.
Ideally, I want that same format I always have with the boxes and stuff like that. That's probably the way to go. If you're running short on time, you may lose a little bit of points or something like that. If you can't get in that format, my recommendation is if you have the time to get in that proper polynomial over polynomial, do so.
Say as much as out of
It should all polynomial over polynomial. I don't want a 1 over s on the bottom. Question. These are the same value of c though. C1 is equal to C2 is equal to C. It's just a constant. I did not define them as C1 and C2. I just said they're both C, right? Both masses are M. Other questions for this before we move on? All right. Let's very briefly go through homework 2, number 4. I only want to talk about this one a little bit. Problem number 3, I should say, rather. Okay, we have a circuit, and I want to get a transfer function from input to output. Put ground wherever. Ground doesn't matter that much. I guess ground probably should be over here, but whatever. I don't care about that part. Okay, what I am looking for here, let's read the problem carefully. What is the input for our system? Why is it I? The source, right? If I didn't tell you in the problem, right, that's an external source that's putting power into the system, specifically a current controlled power source, right? It's external. The source means a source or sink means it's external, right? That is going to be our input for our system. The output for this is the current of the resistor R1, right? Or was it the voltage? I think it was the current, right? So I, R1 is equal to Y. That is the output for this. I bet that's where a lot of people messed up, is that they didn't read the problem carefully. They used voltage or something like that. All right. So how do we get a transfer function from input to output here? I think I've gone through this with a couple of you guys in office hours, and I know at least one of you was frustrated by how easy this problem ended up being when you actually know what you're doing here. So suggestions, what do we do here? Impedances, right? Or time domain method. I would recommend impedances in this case. I think that's easier, right? So let's just redraw this. I'm not going to redraw the entire figure. Let's replace these with our impedances. Impedance for an inductor, L times S. Impedance for a resistor, whatever that resistor's value is. It's R1 for this guy. It's R2 for this guy. For a capacitor, it's 1 over CS. All right. What do we do from here? What do you guys think? You want to simplify it to get a total impedance, right? We're probably going to end up doing that at some point. So, right? So which two impedances do you want to combine first here? These two, all right? What are these in? Series, parallel, something else? They're in series, right? So we could just add these guys together. Right? May be helpful to actually simplify this a little bit more. I'm not going to do that right now. But we can multiply top and bottom by CS, right? I guess I will do it right now. Right. After we do that, what's the next recommended step? What do you guys think? Can you say that a little bit louder for everyone else? Right? Once we've done that, we just have 3 elements all in parallel, right? So you don't add them up. What do? This is probably, I would say, one of the most common mistakes I see a lot of times. Say again? Close. 1 over the inverse of all of them added together, right? It'd be 1 over LS plus 1 over R1 plus that inverse, right? And then all of that inverse of that, right? And that would give us our total impedance, right? We can go through, and that would look like a transfer function. But is that what we're looking for? Right? Is that what I asked for this problem? I'm looking for input to output, right? Does that impedance represent a transfer function from input to output? No. Right? But maybe it can help us. All right, so we have reduced our circuit down to this. That U of S is a current. Voltage of what? All right, so now you're saying, let's call this V of S. That is the voltage of this entire circuit, right? How does that relate to what we have here? What's V of S equal to? Current times not resistance, but impedance, right? Okay. But how does that help us here? Right. That's another way I could write this. Or what's the definition of impedance, right? That is the key for this problem, is the definition of an impedance. Yeah? Good, right? So they will all have the same voltages, right? But remember, we're looking for output current for that resistor. Right, so let's take it a step back. You're correct, right? What is the definition of impedance? Voltage in general, I'll just put a G for general. Voltage of an element over the current of an element, right? You just said that this V here, right, is the same thing as the voltage over R1, right? So this is equal to V R1 of S, if we were to write that down earlier here. Right? Okay. So how does that help us? Which I? Right? The IR1, right, times R1 is equal to that voltage VR1, right? Or we can take a Laplace transform of this. R1, IR1 of S is VR1 of S, right? IR1 of S was our output, right? Why? VR1 was this. So R1 times our output current is equal to that total impedance times our input. We can now solve this, right? And I'm not going to go through the full complete solution. I'm just going to keep in the simplified form here. It would be the total of S over R1. Did I write that out right? I did. But that's your general procedure. I get this, right? If you know the definitions for impedances, this problem becomes pretty easy. Okay? Any questions on this? All good? All right. We got about 5 minutes left. Let's go through homework number 3, problem number 1. We're just going to talk about this one a little bit here. Let's see. So, homework number 3, problem number 1. We got a voltage source, VI. Actually, VI of S, I already did a Laplace transform of this side over here. Very bad notation in this problem, but shouldn't impact you guys too much. We had an impedance Z1 of S. That was going into our op amp. Right, we also had Z2 of S floating out over here. Right, then we had, I guess I'll write it more properly as RA, and then L times LA of S. Even though we don't need to do it this way, we could leave it in the time domain. And this just connects to a motor. Motor that now has a damper on it, CT, and a torque tau A, as we always do, with motor constant KV. Sometimes I'll write this as just like a connection KB here, or KM, or K whatever, for that motor constant. Okay, and I also labeled this, and this was a little bit of a hint here, VO of S. All right, so suggestions about how to get a transfer function from our input to our output. Our output, I stated, was the angular velocity of our inertia. What's our input to this system? Just VI, right? That's our voltage source. So, suggestions. How do we go about doing this? What do you guys think?
Break it up into parts.
Yeah, that's what I recommend, right? We have very clearly defined op amp side, right? And then a very clearly defined motor side, right? So what is the op amp equation here? We only really need one of it in this case. What is our one op amp equation? V out over VI is equal to what? Right, whatever those terms end up being. Yeah. Yep. Sometimes we will need to use the extra op amp equations, right? Remember, I like circled like 3 or 4 of them for what's important for an op amp, right? But this is the core one, right? And this is the only one that we actually need in this problem, right? So it is perfectly okay if you just go straight to this equation here, because that's all we need here. I'm not looking for you guys to derive the entire op amp set of equations or whatever, right? Okay. So we got a relationship between VI and V out, right? For our op amp. What do you guys suggest we do next? All right, the rest of this, right, is just a DC motor, right? So let's pretend for the time being, V out of S is just like our input voltage to our DC motor, right? And get the DC motor equations like we always have, right? We should end up with the same exact thing that we always do, with the exception of this damper being here instead of load torque, right? So we can get some sort of relationship between our angular velocity and V out of S, right? Which is our input to our motor, right? I'm just going to call this T of S. All right. All we do from here, combine these two equations together to get everything in terms of our input to our output. Right. And that's it. That's all there is to this problem. I want to make it fairly simple, right? So if you know how to build a motor model, right, and get a transfer function for it, and then if you remember our core equation for an op amp, all you needed to know was how to combine them together here, right? The big trick of this problem was realizing that this is an output for our op amp and an input for our motor, right? If you were to break it up into subsystems.
Instead of the issues for S theta S, what's that?
Sure. Is it omega, do you mean? Or some? Yeah. Omega, right? Capital omega. Yeah, I mean, at the end of the day, you just say y, right? Y over u. But yeah, if you want to do it in terms of theta, you can. This problem actually using theta would be more work than necessary, right? Because we don't have a spring here, right? So actually having position, that's like adding in an extra step that you don't necessarily need to go through. It's better to just work in velocity in this case. All right, I think we are out of time here. I have office hours today and Wednesday and also by appointment. The warning is for Thursdays, especially Thursday afternoon. I can't meet for office hours. I'm booked on Thursday afternoons. But just send me an email if you want to meet. Other than that, I'll see you guys Wednesday for regular class. Yes, we're having class Wednesday and Friday as normal. Why?
Job fair.
Okay, if you're going to the job fair, just send me an email and you'll be excused, right? Sit ahead of time, right? Like well ahead of time, send it to me today or tomorrow. That's perfectly okay. Just let me know so I can get a head count.
General question.
Yeah.
Is this to say that the exam will be similar, but the difficulty level will be that assignment will be more than the assignment?
It will be able to be completed with more than enough time in class, okay? So there's an exam instructions, but like I said, there's 3 problems. I think somebody's gonna finish under 20 minutes. I think a good number of people will finish early, and then probably some people will just take the full amount of time, okay? All right. Hold on here. Folks online, do you have any